I welcome you all for my next video on design of laterally supported beam. Problem number 1. Here this is the problem statement. A roof of a hall measuring 6 meter into 14 meter consists of 12 mm thick RCC slab supported on steel I section spaced at 3.5 meter center to center. The hall is having wall of 30 centimeter thickness all around. The finishing load on the roof is 1 kN per meter square and live load is 2 kN per meter square. Design the beam, steel beam, and apply all the necessary checks on design. So here this is a problem. We are designing what laterally supported beam. First we will know what we mean by laterally supported beam. This is an industrial building. If you see here, this is what the beam we are designing. So this is the roof. Okay, this is an example for a beam. So these are various industrial buildings. So where on the beam the RCC slab is resting. So the beam types we can use in the construction are I section, T section, box shape, and again I section, and channel sections we can use as a steel beam types in the construction. The next question is, what is meant by laterally supported beam? If we support the compression flange of the beam by avoiding the lateral movement, there will be only vertical movement will be there. There is no lateral movement. Then that beams we call it as laterally supported beam. For example, here they have inserted the compression flange inside the RCC. So there is no movement of this compression flange along this direction, horizontal direction. There is no lateral movement. Here also they have placed RCC and they have connected using shear key. And here also they have not allowed the this beam. This is written in terms of cross section of beam. They are not allowed the beams in lateral direction movement by giving some bracings. This is what laterally supported beam. So if you see the cross section of beam, this is the I section, where this is we call it as flanges, top and bottom flange. This we call it as web. If we insert this flange inside RCC or shear key, we have various types to avoid the lateral movements. Then that beam we call it as laterally supported beams. If you allow the movement of the compression flange to move laterally, then we call it as laterally unsupported beam. So in this case there will be only vertical movement will be there after the application of the load. Only vertical deflection will be there. There is no horizontal deflection in case of laterally supported beam. This is for your information. Now if you look into the problem statement here, they given a hall measuring 6 meter into 14 meter distance. First is X dimension, second one is Y dimension. I have written that industrial building configuration here. 6 meter by 14 meter is spacing at 3.5 meter. Here we have 1, 2, 3, 4, 5 beams. 5 beams. And we have written what the cross section of the beam also. If you take the cross section here, if you look from this side, if you look like this I section, this is RCC slab 120 mm thick. This is the I section. So now here we need to design the beam like RCC. In case of RCC design, we have fixed depth and width of the beam. We check it for deflection, shear, and moment capacity and all. Here also we should do the same thing. We need to take the steel section from the selected steel section based on the moment resisting capacity, and we need to check the capacity for shear, moment, deflection, and so on. So here this is the building. Now assume that we have selected this interior beam, this beam. So now our question is, so on this beam how much load is acting, we should calculate. So before that, the effective span of the beam is, we know clear spans bearing. Clear span 6 meter, bearing is 300 mm wall, all around we have. So if you convert into meter, 0.3 meter, total 6.3 meter. Spacing of the beam 3.5 meter center to center. Thickness of RC slab 120 mm, nothing but 0.12 meter. So we should take, so if they're not given, we can assume the unit weight of RCC, that is density of RCC, is 24 to 25 kilonewton per meter cube. Now the first step here is we need to compute the load on the beam. How much load is acting on the beam? First we need to take the slab weight. The slab weight is, how to take the slab weight? The thickness of the slab into density. We're going to get in terms of meter square area. So here we're getting what? I have taken 24 of density of concrete RCC, getting 2.88 kilonewton per meter square. For finished load here, they're given 1 kilonewton per meter square. If they're not given, we need to assume 1 to 2 kilonewton per meter square. Live load is given in the problem 2 kilonewton per meter square. Total load on the roof coming is 5.88 kilonewton per meter square. If we convert into meter, we need to multiply this value with spacing of the beams. So now load per meter on the beam equal to load from the roof into spacing of beams. 5.88 into 3.5 will go to get 20.58 kilonewton per meter. This is the UDL acting on the beam. So now if you assume the self weight of the beam of I section 1 kilonewton, the maximum depth of the I section having 1.5, so 1 kilonewton per meter is enough. We can assume up to 1.4 1.5 kilonewton per meter as a self weight. That is the available section in the market, the maximum self weight. If you see the steel table here, so this is what IS1 ISWB, Indian Standard Wide Flange Beam, having 600 millimeter depth, having unit weight of 145.1 kg, or if you convert into Newton, the same way here 1423.4 Newton or 1.42 kilonewton. So therefore we can assume here up to 1.4. I have taken 1 kilonewton per meter here. So total design load on the beam is, including self weight, it comes out to be what? 21.5, let's say 22 kilonewton per meter. Now the factor design load on the beam is the UDL 1.5 into 22. We need to multiply with the passivity factor, load factor. So that is 33 kilonewton per meter. Now we need to calculate the maximum bending moment due to this load. So since the given is simply supported beam, UDL is 30 kilonewton per meter. So total effective length of the span is 6.3 meter. So simply support maximum bending moment would be WL square by 8. So 33 6.3 square by 8 will go to get 163.72 kilonewton meter. Now based on this value, we need to calculate the plastic section modulus. Based on that, we need to choose a section from the steel tables, from the code book. Now calculation of required plastic modulus according to class 8.2.1.2. If you see the code book here, 8.2.1.2. So we should look into the the section 8 chapter, design of members subjected to bending. So in that chapter is 8. I'm looking here 8.2.1.2. Here this is a formula. So now we are assume starting as beta b equal to 1. So what we want is that b, we know bending moment, external bending moment, that is design bending moment we know. Fy is 250, gamma m naught is 1.10 from table number 5. If we take this formula and substitute the values, Zp required will be what? M in terms of Newton I have substituted here 163.7 10 power 6, and load gamma m naught is 1.10 from table number 5. Fy is 250, will go to get 722.36 into 10 power 3 millimeter power 3. So now if we convert into centimeter cube, this will be 720.36 centimeter power 3. So for this value, we need to add 20 to 30% extra for safety and choose the plastic ZP having I section having ZP greater than this value, 20 to 30% greater than this value, from IS 18 2007 table number 46. So if you go to table number 46 here, this they given what the various I sections and the unit weight section area and other details. Here we need to look what plastic modulus here. In our case, what we required here is minimum 720, increased 20 to 30%. I have increased around 25% here, and I have taken a trial section of ISMB 350. So if you look into the table here, IS code ISMB 500, ISMB 350 here. So the unit weight is 52 kg per meter, and the area, depth, the flange width is 140, and thickness of the flange, thickness of the web. And if you see the the plastic elastic section modulus or the elastic modulus here is 779, where the plastic modulus 889.57 centimeter cube. This is in centimeter cube. So this is the section I have chosen here as a tile section. So this 889 is greater than 720, around 25%. So now from the steel tables we can get all these details: height of the beam, that is I section, width of flange, thickness of flange 14.2, thickness of web. This we correct as root radius R1. R1 here is 14 millimeter. This is correct as root radius. Here there is a curved portion here. This also curved portion. This radius we correct as root radius. Here also there is a curved portion that we correct as R root radius. This is width of the flange, thickness of the flange, thickness of the web. Depth of the section total from top to bottom. If you take from here, after deducting root radius, we are going to get effective depth, that is small d. Here and also IXX value from the steel table. Here if you see ISMB 350, ISMB 350 here we are going to get what the details, ZXX and all other details here. Here if you see here 52.4. So width of the flange, thickness of the flange, thickness of web. This is what moment of inertia, IXX, nothing but IZ we call it as. Along XX axis, centered moment of inertia 13660.3, and IYY and other details. We need to write these values from the code book. This is in terms of centimeter cube. If we convert into millimeter cube, we need to multiply 10 power 4. So depth of this is exact depth, not the curved portion. If we deduct the curved portion, remaining will be straight portion. That depth of web will be equal to h minus 2 into thickness of flange plus R1. We need to remember this: 2 times of the flange thickness plus 2 times of root radius. We'll go to get 293.6. This is the depth of the beam, that is small d, effective depth, the straight line portion. Now after choosing the any section from the code book based on the plastic modulus, we need to go for section classification, as we all know that there are 4 sections available in the steel as per IS 800: plastic, compact, semi-compact and slender. We need to check which section is coming for our chosen element, that is I section. So we need to go for section classification according to table number 2 of IS 800. This is the table. So for rolled section, here this is about rolled section, not a welded section. This is a single element. So since this is rolled section, if you go for welding, we correct as welded section. Since it is rolled section, if you see the table for rolled section, we need to take B by TF ratio. If it turns out to be 9.4 epsilon, that will be plastic class 1, like compact and semi-compact. Here if you check the values, epsilon will be what according to the code book. Here epsilon is 250 by Fy, square root of 250 by Fy. Here Fy is 250 in our case, yield strength of the steel. Therefore epsilon becomes 250 by Fy, that will become 1. So now B by Tf. So what is B? Outstanding element of compression flange. We need to take total width of the flange by 2. So that is 140 by 2. Thickness of the flange is 14.2. We are getting 4.92, which is less than 9.4 epsilon, nothing but 9.4. D by Tw, D we calculated here 293.6, 8.1, 36.24, which is less than 84 epsilon. 84 epsilon will getting equal to 84. Therefore the section is plastic. If you see the table here, if you see here for rolled section, B by Tf ratio is less than 9.4 epsilon, therefore plastic. That is what the flange is plastic. If you go for web, neutral axis at mid depth for web of an I or H plus section, we need to see this section. Neutral axis at mid depth is D by Tw 84 epsilon, less than 84 epsilon. Therefore the web also comes under plastic section. Therefore entire I section is plastic. We can classify it as plastic section. So now we can provide this. So we're not supposed to provide what? A slender section. Sometimes maximum will go for compact or semi-compact. Now check for sectional adequacy. So assume itself it is, we need to check the section what we chosen now. Check for we have assumed self weight of the beam is 1 kN per meter, but actual weight is 0.514. We have taken more value, then no need to worry. Plastic modulus required is 720 centimeter cube, but we have provided 889 centimeter cube. Therefore hence the adequacy is okay. So now we need to check for maximum shear force. So calculation of design shear force are simply supported by UDL. We know the formula WL by 2. Here W is 33 factored UDL load, span by 2. You're going to get 103.95 kN. Now we need to check the shear strength of the section. The shear strength should be greater than this. Otherwise we need to revise the section. So how to check shear strength of the section? So we need to check the shear strength of the section according to the code 8.4.1. So this is the formula BP AVFPW by root 3. Yield strength of the web, that is 250. Area is for AV we should take area for arc road section H into TW. H is the depth of the beam and TW is the thickness of the web. So this is what, and also we need to divide by gamma m naught. This is the design shear strength VD, where VD is Vn by gamma m naught, where Vn will be this value. So first you should calculate Vn, then we can calculate Vd. So here written directly Vd, taking partial safety factor also. So FYW root 3 gamma m naught AV. So this is 250 root 3 1.10 from table number 5. Area of the H into TW is 8.81. Multiplied here 10 power minus 3 to get answer in kilonewton. So which is greater than 103. Therefore the section is safe. So here we should take area from 8.4.1.1, that is H into TW. So now we need to check for what? Next thing is check for low or high shear case. So we need to check 0.6 VD, take the value 0.6 VD and check with the design shear force. So if it takes 0.6 VD, that is design shear strength of the section, 0.6 into 371.99, this comes out to be 223.19 kilonewton. Now if we need to compare this value with design shear force, that is 103.95. Since it is less than the 60% of design strength, if it greater than the the design shear force 103.95, then it is come under low shear. We need to check this to calculate moment capacity. Next thing is we need to calculate here is moment capacity. Before that we need to check for high shear or low shear case. Here in our case design shear force is less than 60% of the design strength of the section, hence it's coming under low shear case. Now we need to check for design bending capacity. So how to check design bending capacity according to 8.2.1.2 from the code book. Here we need to look into 8.2.1.2 to check the moment capacity. Okay, if you observe here, when the factor design force does not exceed 0.6 VD, then we need to calculate MD using this formula. If exceeds, we need to design with we need to calculate. If exceed, we need to calculate according to 9.2. See, in our case, since it is low shear case, we can use this formula, MD formula. To avoid irreversible deformation under serviceability loads, MD shall be less than 1.2 ZEFY gamma m0 in case of simply supported. We need to check with this one also. This value should be less than this. We need to check. Before that, this formula will be holds good when d by TW is less than or equal to 67 epsilon. First, we need to calculate that. I have calculated d by TW. It comes out to be 36.24 less than 67 epsilon. So we can use that formula, that is MD formula. This value should be less than 1.2 ZDFI by gamma m0 for simply supported beam. Here beta B is 1 for plastic section. If you see the code book here, they given directly in this formula, beta B is 1 for plastic and compact section. For other section, we need to go by this ratio, ZE by ZB for semi-compact section. So now, if you calculate the bending moment capacity by substituting ZB provided, Fy and ZE, we're going to get 202, which is less than, less than 212. It will going to get in terms of Newton millimeter. If you convert into kilonewton, 202 is the design capacity, and the design bending moment is acting is 163.72. We calculate a starting W square by 8 value. So therefore, it's safe in terms of both shear and also in here we calculate moment also. So now next thing is we need to calculate for serviceability criteria. That is, first one is check for deflection. Check for deflection, actual deflection for UDL simply supported, we all know WL power 4 by 384 EI. Here W we should take what service or working load. L is the effective span of the beam, E is Young's modulus of the material, I is the IXX value of the beam. IXX we know, E value we know, and 384 is a constant. So here I have taken what 22 kilonewton per meter, that is a factored load, service load. Here 22 kilonewton per meter converted into Newton per millimeter. Here this in millimeter, this in millimeter power 4, this is in Newton millimeter square. You will going to get 16.55 millimeter. So now delta allowable according to the code is from table number 6. We should take span by 300 for simply supported beam, and that is steel building. So therefore, if you calculate span by 300, you will going to get what 21 millimeter. So here delta allowable is greater than delta actual, hence the design is safe. Now the thing next we need to calculate here is check for web buckling at support. So what do you mean by web buckling? If you see here, this is what web buckling. Due to application for concentrated load or at the support, there will be a normal reaction here. So due to that, there will be a chance of buckling of web. That means this web will go to buckle like this. Due to application of the concentrated load, here we don't have any concentrated load, but in this problem we have what? A support reaction from the simply supported end. Therefore this web will go to buckle. So we need to check for this buckling according to the code. So here this is what the web buckling case. This is what a web buckling case. This is from the support we have taken 45 degree dispersion. This B1 N1 D by 2, that is depth by 2, nothing but in our case H by 2, 350 by 2 in our case. This is the formula we need to calculate according to the code. We need to check the web buckling strength. If you see here, this is the beam of with 300 mm bearing. So here stiff bearing length is we need to take 300 mm. I effective of web we should calculate. Here we should check this strength as a compression member design. For compression member we should calculate FCD and then the strength. Likewise here also we need to do the same thing. We need to treat this like a small column. We need to calculate the strength. So we are targeting for now FCD, that is design compressive stress. To calculate these are the procedure, we should calculate first I effective of the web, that is b1 into t w cube by 12 bd cube by 12, like there's a formula. Here b is 300, thickness of the web is 8.1, cube by 12 you want to get in terms of millimeter, 13.28 10 power 3. So area effective of the web is b into tw, 300 into 8.1, you're going to get answer. This radius of gyration here is square root of I by area. We know the radius of gyration formula I by a. So I effective of web, I area effective of web, we're going to get 2.33 millimeter. So now effective length of the web you should take as 0.7 types of d. Here d we calculate a starting stage, that is what, 293.6, and we know slenderness formula d effective by radius of gyration. If we substitute d effective 0.7 d and radius of gyration, here we're going to get 88.2420 slenderness ratio. For this ratio we need to take FCD from table number 9C from IS 800 2007. If you go for IS 800 2007, we should take always from table number 9C. Here this is 9A, this is 9A for buckling class A. 9B, we should see here 9C, design compression stress. So here in our case lambda value is how much? Lambda value is 88.20. For FY 250 grade still we need to see here. So for lambda value 88 it will come here. For FY 250 grade, this is 250 grade steel, I have taken 136 into 120. So for 80 136, for 90 121 grade steel from table number 9C. So if you calculate that value, after interpolation is going to get 123.979 Newton per millimeter square. So here the buckling strength of the web is the formula. Here B1 plus N1 TW into FCD. Here we have in 8.7.3.1 in the code book. 8.7.3.1. So this is a web check. So here this is the formula B1 plus N1 into TW, the cross sectional area, into FCD we need to multiply, where N is the dispersion angle at 45 degree, B1 is the width of the strip bearing length. We calculated already. So what is N? N here we should take, if we see here, N is what, this much. If you take 45 degree dispersion, this N1 becomes what? D by 2, that is H by 2. In our case 350 by 2. Total depth of the beam by 2, 175. So B1 is 300, TW we know. So just calculate here. So you're going to get what, 475 in terms of kilonewton, which is greater than the maximum shear force 103, hence safe against buckling. So in exam if you not mention for all necessary checks, we have no need to check for buckling. If D by TW if is less than 67 epsilon, no need to check for buckling. The the web will be safe in buckling, no need to check. So next one is last check we need to make here is check for web crippling or web bearing. So if you see a figure here, this is what crippling. So there will be a local failure due to application of what, from the support or the concentrated load. Here we need to take 1:2.5 slope dispersion, where in the web bearing buckling we are taken 45 degree dispersion. This is B1, this is N2. This one also we need to calculate from according to the code book. So now if you see the problem here, this is the formula where we need to see 8.7.4, 8.7.4 here. This is check formula, web crippling formula, B1 plus N2 TW comma M0. B1 is stiff bearing length, N2 is length obtained by dispersion through 1:2.5 dispersion, thickness of the web FW, thickness yield stress of the web, that is 250. So if you go for N2, this is the formula 2.5 into R1 plus TF we need to take. This value here is, if you see the code book here, we need to take what, N2 length obtained by dispersion angle. If you see the figure here, what is N2? This value. Or we need to take root radius plus some extra value, that is what, TF. So 2.5 into R1 plus TF, we're going to get this value 70.5 mm. If substitute here multiply by 10 power minus 3, you're going to get in terms of kilonewton. So this is what web crippling strength of the web. So this strength is the resistance capacity is greater than the shear force. 103 is the maximum reaction going to occur in the beam. Therefore, the beam is safe in terms of crippling also. So since we have checked serviceability criteria, that is deflection, and also web buckling, web crippling criteria, the moment criteria, and shear capacity criteria, in all the cases the beam is safe. Therefore, the section ISMB 350 at 52 kg per meter. What is this 52 kg? For 1 meter Indian standard medium beam having a depth of 350, it's having 52 kg per meter. This is a unit weight can be used as a beam element for the given problem. So thank you very much.